Okay, so now I'm going to talk a little bit about chain reasoning and how we can use it in neurosymbolic energy-based models. So we can see chain reasoning as a form of getting a result for an input using other inputs results as a reference. For example, in this rule that we already see on Damian's explanation, to get the class for image 2, we use the results from image 1. So we already saw how energy-based model functions encode dependencies between the inputs x and the outputs y. And I want to say that we can have two different categories of these functions. The independent ones, where you can calculate the energy function for each component of the vector y separately from the energy function of the other components. And the joint energy functions are the ones where are not separable over y. So how this affects our model? Well, since in the independent energy function we can have separable energy functions, we can have the result for a component separate from the result for the other component, so we can infer the class for both separately, so the inference and the learning can be done faster. But the issue with this type of functions is that it cannot use joint information that may improve the predictions. On the other hand, we have the joint energy functions, where here we can encode dependencies between the output variables, leading us to better results. But we have more calculations and more variables to learn. Here, NeuPSL can use scalable convex inference and have a really good performance, even though it needs to do more calculations. Here we have an example. It's the same one as Damian already explained, where we have an image of an animal and it needs to decide if it's a cat, a dog, or a frog. For the independent energy functions, we have only one image as an input, and then the output is going to be just the label, cat, dog, or frog. But for the joint energy function, the input is a pair of images, and then also the output is going to be a label that is going to combine all the possibilities from cat, dog, and frog, for example, cat, 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 dog, cat, frog, etc. So here we can see that for the first example, the image number 2, the energy function is lower for the label dog. So in this case, the answer is going to be dog. And for the image number 1, the energy function is low for the label cat. But when we have the joint energy function, the model can use external information to know if both images are from the same entity, and here it decides correctly that both pictures are from a cat. So now I'm going to explain a little bit about the experiments that the author of the paper did to test this model. What they did was a comparison with logic tensor networks, convolutional neural networks, and deep problem. This last one is in the same category as NeuPSL. It uses neural networks and combines it with probabilistic logic using Prolog, that is an extension of Prolog. They also implemented two different versions of NeuPSLs for these experiments, the latent variables, one using constraint learning. Then the problems they used to to test these models are MNIST-1 and MNIST-2, and they evaluate accuracy, inference time, and how joint inference and learning can provide better results for NeuPSL. So the problems they have to solve for the models are two canonical neurosymbolic tasks. They are pretty simple. You have as an input an image of a digit, and both problems are addition equations that need to be resolved. And also as an input, you have the label of the number the summatory represents. The difference is that the first one requires only two images, since it's a simple equation, and the second one you have four images to represent two different ratios of digits that need to be added. Okay, so here I wanted to add this example to explain better how we can use latent variables in a real example. We don't have to explain a lot of this model, but the idea is that you can see that here they use only the neural prediction to know which class is going to be associated with the image. And then for the latent variables version, what they did is they added a new predicate called digit that represents the probability that the class given by the neural network is the real digit that the image represents. So what they do here is increase the energy function, the value of the energy function of conflicting solutions between the neural network and the symbolic rules we have here. Something else we can see is that they have to duplicate the rules and the constraints. They are the same one, but instead of using neural, they use digit, and they don't have a weight since they represent hard constraints. And also, during this version, the number of potential is duplicated, and you have more variables to learn and to take in mind when doing the reasoning. Something to add is that this is only explained for MNIST-1, and if you want to see how they did for the MNIST-2, you can go to the paper's appendix. It's a different implementation. They don't use digit as latent variables, so yeah, you have it there. And also, if you want to see all the setup for the testing, you can go there, because here I'm going to concentrate only on the results of the test. So the first test is the inference time per addition, and they only compare here deep problem, since CNN and LTN for inference, they just make a feed-forward pass through a neural network, and that time cannot be compared with the complex inference that these two models do. So as an overview, you can see that NeuPSL is 2 to 3 times faster than deep prolog. And we can see that for the MNIST-1 task, the better version of NeuPSL is the one that has constraints, because we already saw that it has half the number of symbolic potentials and decision variables, so the inference requires less time. And for the MNIST-2, even though we didn't see how they implement it, they got a model much more smaller, because they got to a more concise set of symbolic potentials on the model. And even though they have more variables and everything, this version performed better in this problem. Okay, so now they tested the accuracy of all the models, and we can see that NeuPSL is the highest performance model, or it's within a standard deviation from the highest performing model. And also we can see that it has a really low variance on the results for almost all the cases. So everything I explained until now was done using unique set of images. And to really see the power of joint inference and learning, what the authors did was to add duplicated images to the sets. So here we can see how this changes the amount of labels we will have. For example, in the first part of the image, we have two different images for the digit 0. So here are all the possible labels for the output. But when we reuse the same image for the 0, then since this image needs to satisfy both equations at the same time, the amount of possible answer is reduced. Okay, so here we can see the results of the test with the overlapping images, and we can see that per task they tested 3 different numbers of unique images, and for each set they were incremented the number of addition, so was incremented the overlap of the images. And what we can see here is that NeuPSL again has almost in all cases the best performance, and it has low standard deviation than PSL. We can also see that both the ProBlog and NeuPSL are benefits taking advantages of the overlapping and the joint information. So they are getting better accuracy when the number of overlap increases. So now let's wrap up this presentation. First, we wanted to place NeuPSL in the Kautz taxonomy, since it's something we learned in the first lesson. And we said that it belongs to Neurosymbolic category, since we have different tasks done by the symbolic and the neural modules, and they communicate to improve the reasoning. And then the possible uses for NeuPSL are all the cases where we have low data available. Because I forgot to mention this, but in the examples we saw that here the amount of data available was really low, like 40 unique images, 75 and 150. And even though we have really low amount of data, the accuracy for the model is really good. And then when we have overlapping of the data, or we can have a form to relate the different outputs. And the last final conclusion is that NeuPSL uses statistics, logic, and neural networks to outperform existing methods on joint inference, and as we saw, with lower variance in low data settings. And we also know that neurosymbolic computer allows interpretability and reasoning through symbolic knowledge, and it provides robust learning and efficient inference using neural networks. So that's all. Thanks for listening, and feel free to ask any question you have.
Can you hear us?
Yeah.
Can you explain a little bit on like the overlap of data? What does that mean? On slide 44, I think. The last couple of slides.
Sorry, what was the question? Explain.
On the slide, possible uses for new PSL is that one of the three cases is exists some overlap of the data. What does overlap of the data mean?
Okay, so it means that they reuse, like here, the same image of a digit for different equations. So an image is going to need to satisfy multiple additions. So the labels, the possible labels are reduced. That's what it means. So what affects here is what Dami said. The omega part of the equation is reduced here. This one. So you have less combinations of possible values. I don't know if that answers the question.
Correct me if I'm wrong. So you're saying that when the training goes deeper, the neural network can predict like different, let's say, different versions of zero in its image, and then you just replace multiple zero image with one zero image, so that you limit the space of the all possible cases. Is that what you said?
Yeah, I think so.
Yeah, I think that comes with it, the cost of it's a more expensive computation, because you have like let's recall, for example, the case of the image of the cat.
Yes.
Yes. You can see that in that case, one pass of an energy function leads to three possible values, right? You calculate three different energy states. But in the second case, when you have a joint prediction, you have like a lot more possible outcomes of the energy function. So that's more costly in terms of computation. But at the same time, if you can reuse some images, I am assuming that this is not so costly. So what it's saying is it can take advantage of reusing information, and it will give you a more precise response with a not so much of a heavy extra computation. At least that's what I understood.
Yeah, if the question was how did they overlap, so what they did, they took n amount of unique images, and then they took m amount of duplicated images. Then they created equations. Everything was randomized, and then here is an approximation of the amount of overlapping you have, since you don't decide which equation you take for the training and the testing. So yeah.
I read another question.
On slide 32, why did we take the minimum of the energy function in the first one, and why did we take the maximum of the energy function in the second image?
How did they what? Sorry?
Why did they take the minimum of the energy function in the first image, and why did they take the maximum of the energy function in the second image?
I think they took the minimum. In
No,
both cases, the minimum.
Yeah. So the difference is that this answer for the joint energy function is completely wrong, because this function is able to use the joint information to know that both are a cat. But in the first example, it thinks that the first one is a dog, but it's a cat.
Right here it makes a mistake in the upper case. It predicts the image number 2
Yes.
which is actually the first one, so that's a little bit confusing.
This one is wrong, right?
Yeah, it's image number 2. The prediction would be that it's a dog, but it's really a cat. But as you can see, it's the not clearest image. The image number 1 is much clearer. So when it does the joint energy thing, it takes advantage of that the image number 1 is not clear, and it's able to use that information to predict over the other one.
Okay, understood.
Yeah. Can you go to slide 15?
15.
13. This one.
1.5. Yeah. It says neural probabilistic.
15. This one.
So here you said that if you consider weight as 1, it is hard constraint. I didn't understand why.
No, this is not a the difference between hard and soft constraints if they have a weight or not. If they don't have a weight, it's assumed that the weight is 1. And basically,
Here we have an example.
So if you're in a state where you are able to apply that rule, then you have to apply it. In any part of the computation of your program, it can never happen. In this case, for example, that image 1 is a digit and it has a higher value than the sum of image 1 and image 2.
Yeah, this has to be true.
Always.
Yeah, like your answer cannot contradict this rule. That's what a hard constraint is.
So if they do have a weight associated to it, then at some point of the derivation of a program, you can choose to either follow one rule or the other. So it's not that you have always to follow one rule. The neural network basically decides which rule to apply.
Yeah.
When does the training happen in the case of this? When does the training happen exactly?
The training.
At first, you have so first it's like this is like any like in any learning model. First, you have to train with some data, and then you can do inference. But when you train, you do both, right? You train and then do inference. But the difference is that when you train, you do have the correct values for Y's. So yeah, basically it's which variable you optimize. At first, you want to find I'm assuming that you start with random a set of random training parameters for WNN and WPCL, and then you first update those values using sets of X and Y's from the correct examples set. And once you stop training, you freeze WNN and WPCL, and then you have new pairs. You'll have inputs X variables, and then you go from the learning process to the inference process and try to find the best Y, but you already have this WNN and WPSL frozen.
Okay, so in this case, if we have multiple Y's after we have frozen the model, then those will not be considered in the overlap.
Could you repeat, please?
If we have multiple Y's during the inference process, multiple Y values, then they will not be considered in the overlap, right?
I don't know.
I cannot hear. I don't know what was the question. It's really noisy when you speak, that's why.
Should we type it?
Yeah, just type it in.
Yeah, till then someone else can ask.
Yeah, another question.
So if we have like a kind of image, and then the Y is the data, the set that you contain with the knowledge, that if it's a cat of image, and one of the set is called cat, and another one is called a picture. Does those constraints satisfies at the same time? Is that correct? Because it's also a picture, and then it also the picture also contains a cat. So what will happen if both conditions are satisfied? And then what will the loss function be calculated on? Is your question.
Stephanie, you want to put the slide where the example of the cat is?
Yes. So you said you have a cat,
Yeah.
an image of a cat, and you have a rule that says this is a cat, and another rule that says this is an image, right?
Yes.
Yeah, but you already know that the input is an image, so it doesn't make sense to have a rule.
So
I think maybe if you have an image that says that or of a cat, and then you have two rules. One that says, for example, here that the class of the image is a cat, and then another one that says that the image is a dog, for example. Then that's going to be represented in the weight of the rule W, and then in all the calculation of the energy function and the losses, you're going to adapt, and you're going to know which rule gets you to the low value.
So and if you have constraint rules and those constraints make something that is contradiction basically, then the model will just output the probability of 0.
So maybe I can elaborate a little bit. So if you're in a multi-class classification problem, yes, like there's a cat and a dog in the image, is the ground truth energy, the Y for that, how does that look? Is it just like both the cat and the dog are high up and everything else is like at 0? Is the Y not, because is the Y a histogram or a probability distribution?
I mean, that's probably going to depend how the model was trained and the examples and everything else. It is possible that if you have a cat and a dog, then you'll have low energies for cat and dogs. And it is possible that if they're both of them, then the model just won't recognize anything and just give you a high energy. I don't think there is
it depends on the labels you have, because if your model is trained to know 2 different animals in the same picture, it's different than having a model that is trained to know which animal is in the picture, like this one.
Maybe an interesting experiment could be doing joint inference between images that have one animal and other images that have 2 different animals, possibly one of them the same one that in the first image, and see what happens in that case. I think that maybe could be an interesting experiment.
I had a question here. Oh, hey, our other question got typed in. I'll wait on that.
Oh, sorry. Let's see. In the case of inference, when the model is frozen for the new Y values, new inference values, do they get considered while calculating overlap? I think that if you are doing inference and the parameters of the model are already frozen, then you don't. The idea is that you don't have the Y values. You want to predict the Y values.
We don't calculate overlap, I think. Like we use the overlap of the information of the input and output to get new prediction, but the model doesn't know if the data overlaps. For example, here you have 2 images, and you can calculate if they are probably the same entity, but you don't know if they are overlapping, they are the same image or what.
I think you get an advantage on the overlap because if you are going to predict something with a neural network and you pass the same 2 values, the same value to the neural network multiple times, then the inference process is possibly going to be faster. I don't know, maybe they use cache cache
Like
memory
it
is better.
doesn't have to be the same value, but there needs to be a way of relating two inputs to take the advantage of overlapping. So here in this example, Dami says that you can know if they are the same entity because they were taken from the same device, for example, in a short period of time. But it's a probability, you cannot know.
So with the joint reasoning, the experiments, did it perform better using joint reasoning? Because it looked like they were two different experiments that you showed both.
Yes, they were different because without joint reasoning, they use a lot of addition, as you can see here. For the joint inference one, they just use a couple of images.
Right, they use a
Yeah,
much
you
smaller.
can. Yeah, it's a really small data set, but this was the idea. They wanted to see how it performs with raw data. So yeah, you cannot compare this experiment with the other one.
Because I thought it was kind of weird to see how poorly the other methods, some of the other methods did when you had overlap information. You think everything would have done at least a little better.
Yeah, but here you can see that CNN and LTM, it doesn't have enough information yet to perform well.
Oh, okay.
Because here they only have 150 unique images. So imagine that for MNIST R2, you need 4 images per equation. So you have, I don't know, maybe 50. Yeah, like because you have more images that are duplicated. But maybe you have 50 inputs here to train the model. And that's really low for a logical tensor network or
that makes sense. Did they have an intuition on why the deep problem did well also in this case? Does it also use joint information? I'm not familiar with that word. Did they just mention anything?
No, they only said that they use the same idea of having probabilistics with neural networks. So I guess they also have rules with probabilistic weights, and then somehow they use neural networks results as predicates. But I'm not sure. I didn't have a look.
Their claim is that they're very similar, so they have very similar performance, and I think that what they claim to be an advantage over NeuPSLs that the inference time, the previous slide.
Yeah, our inference time is
much lower. It's much faster. So.
Yeah, for them it's lower.
We have time for maybe one more question. You guys want to fight for it?
What?
Okay, go ahead.
Okay. I was asking. Yeah, he was asking.
So, my question is, so in the experiment setting, like the data size is less than 225. So the CNN in the benchmark are not pre-trained, right? So in the experiment, they basically try to train the CNN with like 200 training examples. Then I assume that the neural network used in this framework proposed by the authors, is it like a really simple, like 3-layer dense network or something?
You're saying that it's
no, I
That's a
have
fair
the
point.
specifications here. Let me see.
And I feel like
I don't remember.
8 layers.
Of dense network,
Sorry.
just dense, like fully connected 8 layers.
No, each of one is different. The first one is convolutional, the second one max pooling, the third one again convolutional.
But I think he's asking about the neural networks using on the NeuPSL. I'm
Yes.
checking just
So
right
for
now.
the MNIST-ALT model, they specify 8 layers, and they mix max pooling, convolutional, and fully connected.
Yeah. Yeah, that, if you let me share my screen, I have
Yes.
the
paper.
Yeah.
So it's page 26.
Yeah, I have it. Sorry. This is the settings of the
You got that right.
networks. So the answer to your question is that neither. I mean, that's a fair question, considering that CNN is not pre-trained, but given these specifications, we could say that neither of the models used was pre-trained. NeuPSL incorporates like previous knowledge in the form of rules, and it would be interesting maybe to compare some pre-trained neural networks with these neurosymbolic models to see like 2 different ways of incorporating previous knowledge with pre-training and with the use of logic rules. That would be interesting. Maybe pre-trained models would perform better with lower amount of examples.